Welcome to this final vodcast on IB Physics topic 4 wave characteristics, or 4.3 wave characteristics, where we look at polarization. So the understanding here is polarization, and there are 3 skills. We've got to describe methods of polarization. We've got to sketch and interpret diagrams illustrating polarized, reflected and transmitted beams, and we've got to solve problems using Malicious Law. And we'll be revisiting somewhat I intensity is proportional to V amplitude squared, and also looking at this other equation on the bottom right. So polarization is a property of transverse waves only. One of the big themes of this topic is that pretty much everything you can do to any kind of wave, you can do to all kinds of waves, or they share properties. And that's true to a large extent, but there are some exceptions, and one of those is polarization. Polarization really does just apply to transverse waves only. And generally, every example and situation that I have come across, I'm not going to say it's the only possible ones, but almost all of them, we just refer to electromagnetic waves, such as light, although other types of EM radiation, such as microwaves, also crop up occasionally. The diagram, or the picture on the right here, shows an example of a polarizer in use. And all it has is it's sort of what it looks like is transparent, or mostly transparent but shaded, so things look darker if you look for a polarizing filter. But if you put 2 of them together, they can appear significantly darker, and that darkness will vary according to the angle. This diagram tries to illustrate what's happening. Most of the time, light, EM radiation, but we'll use light as our example, when created by most methods, such as hot objects, will come in unpolarized. Polarization refers to the angle at which the transverse waves are happening. And so unpolarized light, the angle of the transverse waves, the electric and magnetic fields, is in all directions. It's not polarized. It's a complete mixture of all directions. If we pass that through a polarized material, then only certain directions are let through. And light that is only that light which matches the correct direction of a polarizer is let through. Now, since unpolarized light is equally in all directions, that means that 50% of the light is let through, because 50% of it is in other orientations, and that's why you have sunglasses made out of polarized, because things appear darker. And so you have unpolarized light incident on the polarizer, and then polarized light, which only has an orientation, transverse orientation in one direction of its electromagnetic waves, comes through. So unpolarized light over here, polarized light over here, because it has passed through a polarizing filter. And in terms of the amount of light that's passing, 50% will get through. And previously, all directions, now those oscillations are in one direction only. As a consequence, if you pass through polarized light through a polarizer, what happens very much depends on the angle. So in this diagram, we have unpolarized light incident on A, the polarizer. It then becomes vertically polarized, matching the angle of polarization of the polarizer. And we get through another piece of the same material, the same polarizing filter. Now, the second and subsequent polarizing filters in a sequence like this is known as the analyzer. So polarizer, analyzer, spelling with Z or S depending on American, British, whichever you prefer to use. Officially, the American uses the IB uses the American spelling here. Okay, so vertically polarized light then hits analyzer number 1. Now, analyzer number 1 is also vertically polarized, which matches the angle of polarization, so it passes straight through, no problems. However, when it meets polarizer 2, whose angle of polarization is horizontal at 90 degrees, right angles to the angle of orientation, it doesn't have any or part of its wave polarized in this direction, so this blocks out the light completely. And that's what's happening in this picture here. these two polarizers are at different angles. They're not at 90 degrees at each other, because if it was, this would be completely blacked out, but they are significantly different, so only a very small amount of light is able to pass through. So here we have some polarized sunglasses blocking some of the light. I just wanted to show you a couple of the applications of this. One application is for things like fishing. Now, as I said, polarized light out in the daytime is generally unpolarized, but one of the ways that light can become polarized is through reflection. So here we're looking at some water, and you can see there's some pondweed underneath the water, but what you're actually seeing is partially light reflecting from the pondweed and coming out of water, and also light reflecting from the surface of the water. The light coming from underneath the water is unpolarized, but the light that reflects from the water is polarized. If you put the polarizing sunglasses on, then the light that's polarized, the reflected light from the surface of the water, is cut out. The unpolarized light comes through. So the entire scene is a bit darker because it cuts out some of the light, but it preferentially cuts out the polarized light, so you can see the underneath a lot more clearly. As well as water, window glass will do the same thing. Glass will do the same thing. So on the left here, you can see some light coming from inside the room through the window, but that is basically masked by reflected light off the glass. However, the light coming from inside the room, reflecting from the curtains and the wall, is not polarized. The light reflecting from the glass is polarized. Adding a polarizing filter to your camera or wearing polarized sunglasses will get rid of the reflected off the glass light, allowing the inside of the room to be seen much more clearly. And another use for photographers that's not quite so creepy is that some of the light coming from the sky, the blue sky, is polarized depending on the direction it's coming from. And so if you put a polarizing filter there, it can make that blue sky look darker, which gives your photographs a better look. It doesn't affect the clouds so much. I mean, it makes everything a little bit darker, but it increases the contrast between the sky and the clouds, making for a better photograph. So that's another application. Now, Malicious Law is a way of calculating the intensity of the light that happens when polarized light passes through an analyzer, through another polarizing filter. So the polarized light comes through here, okay, and it's oriented in this direction. And then you have an analyzer whose polarization is offset by angle theta. If theta is 0, then the amplitude of the wave will continue completely unchanged. If theta was 90 degrees, pi divided by 4 radians, then no light would be transmitted. But if it's any other angle, then some light will be transmitted, and the amplitude of the transmitted light will be equal to A0, the initial amplitude, multiplied by cos theta. Since intensity is proportional to amplitude squared, as we saw earlier in the course, then the intensity of the transmitted light equals the intensity of the incoming light multiplied by cos squared theta. That's Malicious Law, and it's in the data booklet. Couple of questions. Here's one from 2011 that I quite like. It tells you there's incident light passing through a polarizer and that the transmitted light has an intensity of 2. So it's incident with an intensity of 8, transmitted with an intensity of 2. We then rotate the polarizer by 90 degrees. What's the intensity of the transmitted light? Well, what's the alignment of the polarizer compared to the incident light, the incident polarized light, plane polarized light? Well, it's not completely aligned, because if it was, it would be 8,8. It's not 90 degrees, because if it was, it would be 8,0. Instead, it's partially 8,2. So when it's rotated through 90 degrees, what does that mean? Well, let's look at the possible answers, because this is a good example of a question where you don't have to do any maths, you just look at what the possible answers are. It can't be 0. A is impossible. It would be impossible because if it's to get 0, it would be tilted by a small degree, and it would only be possible at 0 and then 180 degrees from that. So A is 0 because it's not already 0 or 8. I mean, if this was to be 0, then this would be 8. put it that way. It can't be 2, because it can't be the same if it's being rotated for 90 degrees, and it can't be 8, because if it was 8 here, then it would have to be 0 here. So the only possible answer here is, as we just saw, C, which is 6. Question 2 is actually talking about microwaves. The microwaves emitted by the transmitter are horizontally polarized, and then the microwave receiver contains a polarizing filter. When the polarizer is at position W, as shown, it detects maximum intensity. It's then rotated through 180 degrees about the horizontal dotted line. Sketch a graph to show the variation of received density with rotation angle. Well, as the question tells you, the maximum is at 0. If it goes through 180 degrees, then it will be lined up again. So we'll have another maximum here at 180 degrees. And when it's 90 degrees difference, as the equation I equals I0 cos squared theta shows, it will be 0. 0 at 90 degrees. So the graph that we're looking for is something like that. So have the cos squared variation as shown, maximum down to 0, back up to maximum. It's not cos squared, it's not cos because it doesn't go underneath. That would be meaningless. You can't have negative intensity. It has to be cos squared, it has to be purely positive, and with a 0 at 90 degrees for the full 2 marks. Okay, so we've looked at polarization. We've looked at how polarization happens. We've sketched and interpreted diagrams, and we've solved a problem or two using Malicious Law. Thank you very much.